things. I've changed up. Next time we are not doing a lab. I pushed it back to the next week. So next week we'll have just a page to finish up on notes, and then you can work on sapling, getting your lab notebook ready, whatever, get it in. Okay? Couple other things, just pointing out, extra credit, possibility you can bring me 10 paper towels for 10 points into quizzes. I've also opened up the CE family quiz till Friday. So if you didn't take that or need to retake it, you can do that. I have lengthened the time to 60 minutes. Okay? 30. Okay, so the other thing is make sure on Friday you need to have up through 6.4, including 6.4, done in sapling to be done by midnight, and quizzes. Any quizzes up through 6.4 you want to redo need to be redone by then. So today we did 6.4. Next time we'll do 6.5. That will go on the next term. Okay? Make sure that you're finding a day at least or two in between January 18th and the 24th to take this test, this next test. Okay, when we come back, we will be doing 2 labs and then going on to the next unit. Okay, those 2 labs will help you with more with what we're going over today in class. All right, questions? All right, grab your notes and let's get rolling now. We are going to start with Avogadro's hypothesis, and what he did is he held, if we looked at the combined gas law, he held temperature and pressure both constant. And so he found out that V and N are directly related. And if you remember the gas laws, in fact, let's go through them really quick. What is the ideal gas law? What is the equation for the ideal gas law? Pervert. PV equals nRT, right? Ideally, you're not a pervert. That was how you remember it, right? Okay, now, then you had the combined gas law where you took 2 ideal gas laws, solved for R, and set them equal to each other. What was that law? On this side, on the top was what? P1 V1 divided by T1 equals on the other side P1 V1 divided by T2. We dropped out N. Why did we drop out N? It's often hard to find and work with, so we dropped out N. Then we got to Boyle's law. What was held constant in Boyle's law? This is a review, trying to get you where you need to be. It's P1 V1 equals P2 V2, so what's held constant? Temperature, good. Then we went to Charles' law. Prince Charles is under constant pressure, so the equation is V1 divided by T1 equals V2 divided by T2. Then we got to Gay-Lussac's law. I said it purposely wrong because what's held constant? Suck it up a straw. Volume. Okay, so Gay-Lussac's law held volume constant. So what was each side of the equation? What was on the top? P1 on the bottom. So P1 divided by T1, the other side would be P2 divided by T2. That was where we switched, and now they're not related to the ideal gas law. And we worked with this with a straw last time when we did the lab. What was the law we were working with the straw? And the 2 different kinds of gases. I called it Grandma's law, but it's not really grandma. Grams. And what did it have to do with? The velocity, how fast a gas versus another gas moves. Okay, so, and it's related to its mass. So Graham's law on one side said rate A divided by rate B equals, on the other side, square root mass B divided by mass A. Okay, then we hit the duh law, which was what was the duh law? Okay, pressure total equals all the little parts added up, right? And we used it in the lab last time where we took the pressure of the gas is equal to the pressure total minus the pressure of the water, right? Okay, so that was Dalton's law. So Avogadro's law basically said, okay, if the number of moles goes up, the volume goes up. So it doesn't matter what compound or element that I have, if I hold it at the same temperature, at the same pressure, and I have 1 mole of it, the volume is going to be 22.4 liters. So we actually add that into our mole map, and now we have a way to get to volume in our mole map. Okay? That's about all we need to know about Avogadro's. Now we're going to practice some problems. Some problems you might see, or some problems like what you might see. Remember that I hate story problems, and so I'm always pulling out of it, drawing pictures, trying to get it in my head. So I'm going to do that with you right now. So first thing, we're looking for pressure. Since it's the first pressure, I'm going to put P1. It might be the ideal gas law, and I won't need a P1, but I'm just going to do it. The next thing says by 2 moles. Oh, that's an N. I'm probably going to have the ideal gas law because the ideal gas law works with moles. Okay, of oxygen. Okay, I don't know if I'm going to need that, but I'm going to put O2. Confined to a volume of V1, 500 milliliters, at a T1 of 20 degrees Celsius. Right there I stop and say temperature always has to be in Kelvin, so I add 273.15 and I get 293.15 Kelvin. What law do I have? Well, this one's going to have to be ideal gas law because all the other laws I need 2 of something, 2 pressures, 2 volumes, 2 temperatures. I only have 1 of each. So it's going to have to be the ideal gas law, PV equals nRT. And we are looking for pressure. So because we're looking for pressure, I'm going to divide both sides by volume. Now the other thing that I need in my knowns is R. R is a constant. It does not change. So we either put it on a 3x5 card or we memorize it. It is 0.0821 atmospheres times liters divided by moles times Kelvin. That is the units on it. I need to make sure all the units of everything I'm using are the same as the units on that R. So mole, yes. Milliliters, nope, it's liters. So I'm going to need to convert that. So there's 1,000 milliliters in 1 liter, so it's 0.500 liters. Okay, temperature, Kelvin, temperature, Kelvin. So I'm good. Now all I have to do is rewrite the equation so I have it, solve for P, and then plug in. So N was 2 moles, 2.00 moles, times R, 0.0821 atmospheres, times liters divided by mole, times Kelvin, times by temperature, 293.15 K, divided by volume, 0.500 liters. Now at this point, even before I grab my calculator, I double check the units. They've got to cancel except for pressure, which is in atmospheres. Moles cancel with moles. Kelvin, Kelvin. Liters, liters. And I am left with atmospheres. So I know that I've got it set up right. So pressure in atmospheres, somebody calculate that through. We need 3 significant figures. If you haven't got a calculator, you need one. They're just inside the lab here. You can go grab one. As soon as somebody's got an answer, let's put it up and see if we've got a second on it. Do you not have your packet today?
No.
You can grab another one. They're in the CE 1110, and then you can just use it. Yes. Point what? 2.7. Do you have a second on that one? All right. We actually would probably put 96.3. Okay, and that would be atmospheres. All right, so it's just once we get it done, all we have to do is plug it in, right? And get what we need. Okay, let's go to the next one. Did you find it? Did you find one? Let's see if I can help real quick. So I'd hate for you to miss all those notes.
chapter 6, right? Oh, it's the very orange one.
There you go. Okay, so let's take this one. A volume of hydrogen gas. So I've got H2. That's what hydrogen gas is. I don't think I'll need it, but I'll put it down here. In a still contained cylinder. So here's in a still cylinder because I'm drawing my picture. What is the volume? So I want V, question mark. If I have moles of the gas exerts a pressure at a temperature, really quickly change that temperature to Kelvin. Okay, what law? I just pulled everything out. A ideal gas law again, PV equals nRT. Oh, we're going to need R. This time we're looking for volume, so I'm going to divide both sides by P. So volume is going to equal nRT divided by P. Now I've got it. I just double check, make sure my units are what I need. I've got atmospheres, yes, moles, yes, Kelvin, yes, and my should be solving and getting liters. So moles, 0.525 moles times R, 0.0821 atmospheres times liters divided by mole times Kelvin times T, 283.15 K. Sorry, my pen starts to skip over that side of the board. Divided by P, which is 3.00 ATM. Again, double check that my units cancel out, moles cancel, atmospheres cancel, Kelvin cancels, and we're left with liters, which is a volume. So I can go ahead and do my calculations, and it's 3 sig figs. Yes? 4.13. Do I have a second on that? You go too fast for everybody. Nobody can do it. There's a second. Okay. Any problems with this? It's just pull it out, make sure it's in the right unit, and plug it in, right? So if you don't remember the laws very easily, this would be something that you put on your 3x5 card. So you have the laws right there. Okay, the gas laws. Okay, going forward to the next one. Okay, the temperature in Celsius. Ooh. So temperature is a question mark, but I want it finally reported in Celsius. I still have to do the calculations in Kelvin though. Okay, I have to do it in the absolute value scale. Okay, of nitrogen has a volume, 2.50 liters, and a pressure of 300 point torr. And it contains 0.100 moles. So what law am I looking at again? PV equals nRT, ideal gas law again. Okay, so we need R, 0.0821 atmospheres times liters divided by mole times Kelvin. All right, checking the units. Liters, yes. Torr, no. I've got atmosphere. So I need to change torr. How do I change torr? You guys remember how many torr in an atmosphere? 760, good. So I'm going to put 760 torr on the bottom. And on the top I put 1 atmosphere. Torrs will cancel. Somebody calculate that out. Let's get what our atmospheres. Should be 0 point something, 0.3, maybe 9, 0.4, something like that. 0.4? Is that to 3 sig figs? Is it to 3 sig figs?
Well, the exact would be
394 atmospheres. Okay, we want to hold the 3 significant figures it have. We want to keep those. Okay, so this time, what are we looking for? We're looking for temperature, right? And you notice that I'm circling what I want to find so that I want it to get it by itself. I'm going to divide both sides by NR in order to get T by itself. So if I get T by itself, then it's going to be PV divided by NR, plugging in, whoops, I almost did 300, 0.394 atmospheres, times by volume, 2.50 liters, divided by N, 0.100 moles, times by R, remember on this one, when you hit the divide sign, you're going to put parentheses, close the parentheses, and then hit equal. So what are we going to get for temperature? Anybody got an answer yet? Sorry, yes. I think it's going to be bigger than that. So take the 0.394 times 2.5, then divide parentheses and put that all in the bottom and then close parentheses. Anybody got a different answer? Yes. Yes. 120.3, and that's Kelvin. How do I change Kelvin to degrees Celsius?
You subtract.
Good. Subtract 273.15, and that will give me degrees Celsius. And sorry, my pen is skipping on this far side. So it's going to be a minus, right? It's going to be a negative. What is this degrees Celsius I get? 150 what? 152.15. Is it 1.5? Okay. I don't think that's 0.15. What is it? 8.5. Okay. All right. Good. So we get an answer. We're able to get it. Sometimes you got to use a calculator, especially this late in the day. It's okay. All right. So going forward, we got another one. Oh my gosh. Okay. Wait a minute. Grams. Okay, well, I'll put it down here, but I don't have a thing to assign it. 2 grams. Okay, a sample of 2 grams sample of gas has a volume. I know what to do with volume. Equals 1.12 liters. Ooh, at STP, what's STP? Standard temperature and pressure. What's standard temperature in Kelvin? 0.15 K, right? What is standard pressure? 1.00 atmospheres, because we need 3.6 fix. Okay, calculate its what? Molecular weight. Molecular weight is grams divided by mole. That's what a molecular weight is. You're going to need to do a problem like this on your test, so you want to listen. Okay, yuck. What am I going to use? What law? Well, I've got grams, right? I've got grams to put in over here. I just need to find mole. Is there a way I can find mole through the gas laws? Can I find mole using perv-nert still? Because if I don't know N, but I do know R, right? Then I have everything to put into that to figure it out, right? So here I'm solving for N and divide both sides by RT. So N is equal to PV divided by RT. So 1.00 ATM times by 1.12 liters divided by 0.0821 atmospheres times liters divided by mole times Kelvin times by temperature, 273.15. Okay. Doubling, checking, Kelvins cancel, atmospheres cancel, liters cancel. I left with moles. Yep, that's what I want. Mole. Okay, make sure when you go through, divide, parentheses, times through, close parentheses, then hit your equal. 3 sig figs, let's give me how many moles we've got. Do those calculator buttons pumping. We have an answer yet? 0.0499. Didn't like that last 9, I guess. Okay, moles. So now I've got the mole right here. I had the grams, so I'm just going to take 2.00 grams divided by 0.0499 moles. And what number do I get? .0. Okay, well, it asked me to figure out if it was helium, neon, or argon. Helium weighs 4, right? Looking at the periodic table. Neon weighs 20, right? About. And argon weighs 40, about. 39.9, blah, blah, blah. So I have argon, because the others aren't close. Okay? All right, let's move forward. Oh my goodness, it's still container. So I have some kind of container. You know I draw so well. Here's my container. It is a mixture of nitrogen, N2, oxygen, O2, and carbon dioxide, CO2. The total pressure, PT, in the tank is 2,100 torr. The pressure exerted by nitrogen is 810 torr. By oxygen is 920 torr. And what is the partial pressure of CO2? So whose law is this one? This is not the ideal gas law. This is the duh law, Dalton's duh law. So pressure total is equal to pressure 1 plus pressure 2 plus pressure 3 plus da-da-da. So over here, pressure total would be equal to pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the CO2, right? Well, I can go ahead and plug those in right there, or I can rearrange it saying I really want the pressure of the CO2 by itself, so I'm going to subtract nitrogen and oxygen from that side and put it on the other. So pressure total would minus pressure of the nitrogen minus the pressure of the oxygen would give me the pressure of the CO2. Everybody okay with that? So then we just plug in and we say 2,100 minus 810 minus 920 will give me how many torr is equal to the pressure of CO2. What do I get? 370. So Dalton's duh law is pretty fast and easy, right? Not too terribly hard. We okay with that? Okay, we're going on to the next one. Here we have a 250 milliliter sample. Okay, that's volume, right? Of oxygen gas. It's collected by water displacement. Okay, I'm going to make my little water displacement and pretend like there's a little tube here that's bubbling, and we get this, and we get O2 up here. Okay. As a result, the O2 is saturated with water vapor. Oh, there's also water vapor up in here. Okay. The partial pressure of the water vapor is, so pressure of the water is 22 torr. Calculate the partial pressure of the oxygen, so I don't know the pressure of the oxygen. If the pressure total is 720 torr. We did this in lab, right? You had to look up the pressure of the water, and what did you do? Well, pressure of the oxygen is going to equal the pressure total minus the pressure of the water, right? Because they have to add to equal the total pressure. So 720 minus 22 will be 698 torr. I can do that one in my head. That's the pressure of the oxygen. We okay? Yes, no, maybe so. Totally asleep. Got it. Lunch coma has hit. Okay, ooh, this one looks different. The mass of bromine molecule, so okay, I have some bromine, is 160 U. The mass of an argon molecule is 40 U. Compare the rates at which these gases will diffuse. Whose law is all about diffusion? Grandma's perfume. Graham's law. So we're going to have rate A divided by rate B is equal to square root of mass of B divided by mass of A. How do I know which one's A and B? Well, whenever you're given a problem, the first chemical mentioned is A. So bromine, A, argon's B. So bromine is A, argon is B. I do this, I set it up this way so that I can keep things straight. When it says compare rates, that we're actually calling what we call relative, I can spell, rates. They're talking about this fraction right here. So that fraction is a relative rate. So putting in, we would get square root mass of B, which is 40 U, divided mass of A, 160 U. The U's would cancel, right? And we'd end up with square root of 1/4, which would be what? Anybody got an answer on that? Square root of 1/4. Yeah. Okay, 1/2, which would be 0.5, right? So basically, if it's 1/2, then I can look and say, okay, compared to bromine, argon is twice as fast because it'd have to be twice as big down here to get 0.5, right? 1 divided by 2. So the rate of argon is twice as fast as bromine. I don't know what the speed is, but it's twice as fast. So that's what this law gives us. There are no units on this. The units would cancel. Let's look at another one. This one, they don't give me even more. Which will diffuse faster, helium or neon? Grr. Well, I can still use the masses. Helium is 4, neon's about 20. I don't have to use exact because I just can do quick. So relative rates. So if I take helium, rate of helium, versus the rate of neon, then when I do the square root, neon goes on top, so it's 20 divided by helium's, which is 4. So I end up with a square root of 5, which is what, 2.5? 2.25, I think. So which one's faster? Helium. It's lighter. It's going to move faster. Is it 2.4? 2.4? I'm off a little bit. I thought it was 2.25, but we're okay. 2.24, okay. All right, next one.
Wait, so helium would be
Faster.
because it's
Right, so if we look at this, this is basically saying 2.24 to 1. So this is twice as fast, 2.2 times as fast as one of these. Does that make sense? Okay. All right, now I got a riddle for you. I need 2 helpers. I need 2 helpers. Come on. Okay, come on up. Need 1 more. Okay, come on up. Okay, we're going to see which one of these 2 girls are stronger.
Oh gosh, dang it. Helica's gonna be stronger.
Mm-mm. Okay, so I have got these connected by a tube, and right now the valve is closed. This one is smaller than this one. So I want you to look at the possibilities when I open up the valves. Is the small one going to get smaller, or is it going to get bigger? Is the big one going to get bigger, or is it going to get smaller? So there's 3 choices there. I want you to hold up an A, which is a fist, a B, which is just up like this, or a C. I want you to make a decision. You have to choose. Make a decision. I don't see everybody's hand. I'm going to wait. So we're not going to do it until everybody makes a decision. A, B, or C? Okay, got a decision? Okay, I'm going to have you girls, I'm going to hold this once I turn this on, and I want you to massage these balloons to move the air back and forth. Ready? Just don't use your fingernails, okay? All right, go.
What?
Nothing's happening.
Nothing's happening. What? This is weird.
You don't feel anything happening?
No?
I think so. Was that supposed to happen? Okay. Huh.
What happened? Elika can stop you from doing that. Okay, so this side actually got smaller. Why? So actually the small balloon actually got smaller, and you can actually force it to even be smaller if you keep putting more pressure on it. Okay, why did that happen? Why did that happen? Okay, so which one was true? Did they end up the same size?
No.
Did the large balloon get inflated by the small balloon? Yeah. And the small balloon got even smaller. Okay, ever blown up a balloon? When is it the hardest to blow up a balloon? Right at the beginning where it's smallest, because the latex is very tight and you have to stretch the latex. Once you started stretching the latex, what happens? It's easier to blow up, right? So the pressure on the outside of this balloon is a lot greater than on the outside of this balloon. Okay, the pressure on the inside is greater pushing out. So let's look at some diagrams with that. So next page here. We actually have pressure on the outside and on the inside that's acting. So as we did our lab last time and we moved the gas collection tube from the ice cream bucket to the large graduated cylinder, and then we had to equalize it, we were equalizing the pressure inside the glass tube and out to the outside pressure. So when a balloon's being filled, you actually have to push and put more pressure on the inside to make the balloon expand. Okay? When it's filled and tied, the balloon will stay at whatever pressure's on the outside. Have you ever taken a balloon and put it in the fridge or in the freezer? What happens to it? It'll shrink. If I take it out on a hot day, what happens to the balloon? It expands. Okay, so it has to do with what's going on with pressure and the temperature too. When a balloon deflates, what's happening is that latex has more pressure on what's on the outside than on the inside, and we're able to deflate. Okay, so let's talk about some changes in state. We're going to shift gears because now this chapter also includes thermochemistry. And thermochemistry has to do with a lot of things that you already know. The red ones here, these are the triangles down at the bottom of your page. The red ones represent putting in heat energy, which is endothermic. The blue represent taking energy out. Most of you know condensation, evaporation, taking liquid, turning it into steam and back. And melting and freezing, solid to liquid. You probably don't know these words as well. Sublimation is going from a solid directly to a gas, and deposition is going directly from a solid, try again, deposition directly from a gas to a solid. One of the most common uses of that part is dry ice. We take CO2 from the air and we lower the temperature and we make dry ice. It never goes through a liquid stage. It goes directly from a gas to a solid. When we have dry ice and we put it out on the counter, there's no puddle left. It just quickly evaporates off. Okay, so it doesn't go through that liquid stage. In order to get liquid CO2, I've got to have it under a lot of pressure to do that. So we need to know this triangle pretty good and know how putting in heat or taking out heat affects this. So on the next page at the top, there is some things that we need to choose. So if I do condensation, am I taking in energy or giving off energy? Is it endo or exothermic? Endo or exothermic? Taking it from gas and making it into liquid. Am I putting in heat to get that or giving off heat? Exo, I'm getting rid of energy. Okay, what about boiling? I have to put energy in to boil it, right? I have to put a pan on the stove and turn up the heat, right? So it's going to be endothermic. What about sublimation, going from a solid to a gas, like dry ice? Going from a solid to a gas? Endothermic is right. Okay, this next one is wrong, so we're going to talk about it and then it'll put up the wrong answer. So liquefaction is when I take a solid and I make it a liquid. Okay, it's going to be endothermic. It's going to say exo, but it's endo. Okay, what about freezing? Liquid to gas, or liquid to solid. Exo, good. And what about vaporization? Endothermic, good. All right, so you need to be able to tell me what's happening, endo-exothermic. Let's go on to this next one. Whenever we talk about heat and moving and evaporation, we also talk about vapor pressure. And we'll actually go into this more next time, but we're going to just introduce it to start with. How many of you ever made a terrarium when you were a little kid and they told you to put 2 tablespoons of water in and close the lid and don't open it again? Because the water cycle will keep continuing over and over again because of vapor pressure. Vapor pressure is you have a liquid and so much of it goes to gas. In a closed area, it has nowhere else to go, so after it bounces around for a while, it has so much kinetic energy, it loses enough that it becomes liquid again. And then it runs around in here and catches some more and it comes back out. And then falls back down, comes back out, falls back down. If the container's open, the evaporation, it goes out and then it condenses somewhere else. Okay? So this pressure in here in a closed situation is what we call vapor pressure. Now the next couple slides, I'm going to do a lot of vocabulary words so you don't have to put it down word for word, what I put up here, just get the main gist. So we talked about evaporation. You know these from your own words. It's an endothermic process, liquid to gas. What do evaporating molecules carry away from them from a liquid? They carry away kinetic energy. So when we're talking about energy, it's the kinetic energy they're carrying away. What's left behind becomes cooler because of what was there is being evaporated off. So we talk about using evaporative coolers in the summer because as the water goes away, it actually makes the air cooler that goes through it because the energy had to go somewhere. Okay, what is the process above called? It's evaporation or vaporization. Condensation is an exothermic process in which a vapor, exothermic process in which a gas or vapor is changed to a liquid. Not really a solid, but yeah, liquid. Vapor pressure, we talked about that on the last slide. It gave you a sort of a picture view of it. Like I told you, I'm more of a visual learner, so I like to put that in there. It's the pressure exerted in a closed system where the vapor is in equilibrium with its liquid. And on the bottom one, we talk about, again, the kinetic theory rules. So molecules that tend to be nonpolar, they are not attracted or repelled by things, tend to go into vapor easier. That's because things are not holding them. Opposite charge things are not holding them in the liquid. Okay? And they go with a lot less energy. give you a few seconds to finish writing that down. We'll move to the next one. We have a little activity lab at the end. It only takes about 10 minutes, and I think we'll have about 15, so 15 or 20, depends on what we're doing. Yes? With less energy. Yeah, I went a little far on that, sorry. I was trying to make the biggest slide as big as I could, and I'm learning with my projector it cuts off the bottom. So, can't make it as big as I can. All right, we okay to move forward? All right, moving forward. So, think back to your experience with alcohols. Most of you have had experience with rubbing alcohol. You put it on your hand for the you got a sore or something, you're cleaning it out. How does it feel after you've removed that and there's still a little bit of it on here? It feels cold. And the reason why is those molecules are evaporating off, taking the energy with them away. And so your skin feels cold. Here's two sets of chemicals that if you put on your hand, they're both alcohols. One is ethyl alcohol and the other one is butyl alcohol. If I put those on my hands, how could I tell, if somebody didn't tell me which one was which, how could I tell which one was which? The heat difference. Which one would be colder? Would the green or the blue? And why do you think so? This is Graham's law, so think back to Graham's law. What's happening with Graham's law? Which one would give you a cooler feeling? Anybody got a guess? Okay, you said the green. I have two people that say green. Anybody disagree with them? Yeah. Good. She actually was hitting the right thing. I tried to give you a hint with Graham's law. What is Graham's law all used with? It's all about the mass, right? And so the one with a lower mass is going to evaporate quicker because it moves faster. Because it moves faster, it's going to change from a liquid to a gas more quickly. Okay, so this one says it has 2 carbons versus 4 carbons and 6 hydrogens versus 10 hydrogens. It's going to have a lower mass. And because it has a lower mass, it's going to have a higher velocity. It's going to move quicker. Okay, so the blue side is going to feel colder because things are leaving faster. And when they leave, what do they take with them? Kinetic energy, which is taking some of your heat, which makes it feel cold. Okay, so let's go on to the next part where we have a few more definitions to do. Sublimation, this is a new word. Sublimation, remember, it's an endothermic process when I change a solid to a gas like dry ice. Melting point is where we change from a solid to a liquid, and it says equal to the vapor pressure. So that's just the pressure at which we change from a gas to our solid to a liquid. Decomposition we've used before with the types of equations. We're working with heat. Oftentimes when we heat something up, it decomposes. Okay? And there are 3 common substances that sublime. One is dry ice that we've talked about. One is water. And it says freeze-dried. What? Okay, have you ever, you know, the old-fashioned ice trays? I don't know how many of you have them still in your ice freezer. And you put them in the freezer, and they freeze, and you get nice ice cubes. But if you leave them in there too long, what happens to the ice cubes? Does anybody know? Have we seen that? They actually start shrinking. They actually start shrinking, and they get sort of nasty. My mom used to say, we had those too long, chuck it out, get some fresh in there, you'll have to wait a couple hours. You know, but they start evaporating or subliming. And so it will actually sublime. And then iodine is crystals at room temperature, but if you put your hand underneath it, it will warm up just enough and it'll make a purple vapor, which is sort of cool. It doesn't go to liquid. It doesn't like to be in liquid. You'll see iodine tincture that they used to put on sores, and you still can get it to put on sores, sort of that reddish thing. But that is a solution. It's not straight iodine. So it's water with a little iodine in it. Okay, let's go forward. These next 2 things are graphs, and these graphs are going to be very important that you be able to read them. Okay, they use them often on the ACT, on the SAT, and they will be using them on your test. So this first graph is basically a map of any kind of chemical. Every chemical has its own, this is called a phase diagram. So they have their own phase diagram. Always on the y-axis is pressure, and always on the x-axis is temperature. On the y-axis is always your solid. So your solid's going to be next to your y-axis. Your x-axis is always going to be your gas, okay? And then in between, in the y part of the graph, is your liquid. Where they all three meet is called the triple point, because there's one point where I can actually get ice water to boil and give me vapor coming off of it, which is pretty cool. We don't have quite the equipment here to make that work, but we can actually boil ice water and get vapor coming off. Like when you're boiling and you feel the steam coming off the top, you can do that. That is a triple point. So you need to be able to read the graph, and at the triple point they say, what's triple point temperature? Come right down. What's triple point pressure? Come right straight across. These lines right here are known as equilibrium. They're the point of equilibrium between a solid and a gas. So sublimation if I'm going this way, deposition if I'm going this way. You need to make sure you use the right words. So if I say I started at this temperature and this pressure and I decrease the temperature, what happens? Well, at this temperature it will start deposition into a solid. Okay? If I start at this pressure and temperature and I heat it up, what's going to happen? Well, at this temperature it's going to melt, and at this temperature it's going to boil. Okay, so I need to be able to read the graph. Now you'll notice at the very far right of the graph there is a point that is called critical point. At this point, it is hot enough, the molecules are moving fast enough, that it doesn't matter how much pressure I apply to it, I cannot make a liquid. So past the critical point, it's gas, all the way up. Okay, there's nothing I can do to make those except for cool it down, make it into a liquid or solid. So past that point, it's all gas. That's the critical point. So we should be able to read this graph and be able to tell what's going on by following across at any one point. Oh, if I'm given this point and I cool it, what happens? Well, at this temperature, it turns into a solid. It freezes. Or if I have it going forward, at this point, it turns into a gas, and it is a gas past that. By the way, as I heat it up on that one, I come into the critical point, and I can talk about that. Okay, so know what you're hitting at each point. I'm going to actually erase this so I don't actually save that on it. Okay, going forward, the next graph is called a heat curve graph, and we've actually got 2 or 3 pages of this heat curve graph, so we're going to add some more stuff to it. This graph, I can actually get off of it the melting and the freezing point, because those are the flat lines. Okay, so the freezing point is the first flat line, and the melting point, or the boiling point, is the second flat line. Anytime the graph has a slope, I'm heating a phase. So in the pink area, I'm heating a solid. And then when it flatlines, I'm now changing that solid into a liquid. And then when it starts in the yellow to go up again, I'm now heating the liquid. When it goes flatline, I'm now changing that liquid into a gas. And when I get all of it changed into gas and I go to the blue and I start going up, I'm heating the gas. Okay? So that's how you read it. Now, how do we use it? On this one right here, well, let me go back to this one real quick. This flat line here, we're going to use what's called delta HF, which is change of heat of fusion. The flat line where we're changing from liquid to gas, it's delta HV or delta HVAP. That means the heat of vaporization. How much energy does it take to change it from liquid to a solid or from a liquid to a gas, okay? So as we look at this next part, this equation right here is known as a specific heat equation. Specific heat equation. Okay, we're going to be using that equation a lot. Okay, it is used every time my graph has a slope. And you'll hear me say, okay, it's Q equals mCp delta T. I learned specific heat as being Cp. This graph just has it as C, but it was the best graph I could find. Okay, so if you want to put a little Cp right here and here, then you'll know what I'm talking about. This is a constant. but it's a different constant for every phase. So the specific heat of water as a solid is different than a specific heat of water as a liquid, which is different than the specific heat of water as a gas. We'll do some problems with this next time. But that equation doesn't work when I flatline because I don't change temperatures. But I know I'm putting energy in when I'm changing something from a solid to a gas because if I'm still heating it. So at that point, we have to use what's known as a heat of fusion for if we're changing from a solid to a gas and times it by the mass. If we're changing a liquid into a gas, I use heat of vaporization. Now, they can also use the delta H vat or delta H V and delta H fusion or fuse, FUS, or just delta H F. Sometimes they like to use the FUS here because we also have delta H of F, which is delta H of formation. So that gets a little mixed up. But we'll be using this when we come next time to do some calculations. So everybody got that down. You need to make sure you have those basically three different equations. This one, which is here, here, and here, and then the other two here and here. They're basically the same, but just a little different there, depending on what one you use. We okay? There's one more graph that has to do with that one. It's this one, and it's just basically telling you what's happening in each one. So this is for just specifically water. So water will be ice until I hit 0 degrees. At 0 degrees, I'm changing the ice into water, and then I'm heating the water up in the blue area, and then I'm changing the water to steam, and then I'm heating the steam up. This is time, and it's also how much energy I'm adding along. So the more energy I add, the more amount I'm going to get however far I am. Okay? That's as much as we're going to do today. We're going to go talk about the lab. So, whoops, sorry. Slide before this one, yes. Is there anything else you need on that? Okay, would you get your lab out? I gave it to you last time. It's a heat of fusion of ice. I asked you to do the pre-lab if you could before you came. We're going to talk it through. It doesn't take but maybe 5 minutes to do, and then you're back in here doing the calculations. Okay, so listen carefully so you don't mess up. Okay, we good to go? All right, so on your lab, first thing when you go back in the back, you're going to grab a calculator. You're going to grab an Easy Link. You're going to hook to it a temperature probe. Okay, and then you're going to hook it to the calculator. So make sure you connect the Easy Link to the temperature probe first and then hook it to the calculator. You should be getting a temperature reading at that time. If you are not, bring me the calculator because it doesn't have enough batteries. You don't have to go into any program because it will automatically bring up Easy Data, okay, or Easy Link. All you need to do is read the temperature off the calculator, okay? So then at that point, once you've got that set up, as you're going in, one of you grab a graduated cylinder. The other one of you grab a styrofoam cup. I love my styrofoam cup. Okay, most of the graduated cylinders are 50 milliliters. So what I want you to do in your procedure is change that 70 milliliters into a 50. I don't know where all our hundreds went, so change it into a 50. Okay? The person that grabbed this graduated cylinder is going to go over to the hot water, turn on the hot water, rinse it once fully with hot water so you warm up the glass because you don't want the glass to pull the heat. And then you're going to fill it up as close to 50 as you can. Don't go over, just as close to 50 as you can. When you get back to your area, measure exactly whatever it is that you got. Okay? That's your initial volume. Okay, everybody got the initial volume, where it goes. Okay, the other person that grabbed this, so this is going to be hot now. I'm going to do it red. The other person's going to go, and there's some little buckets of ice. So you're going to get a little beaker, little 50 milliliter beaker full of ice. So this is my ice. Okay, then you're going to come back together. When you come back together, you're going to put your temperature probe into the styrofoam cup. You're going to pour your hot in here and get a beginning temp. You're going to write it down. Then you're going to pour your ice in, and you're going to stir with a temperature probe. Now, this is important. At this point, one person's got to be looking at the styrofoam cup and watching the ice. The minute the last piece of ice melts, they need to tell their partner, record the temperature. So somebody's got to be looking at the calculator, the other person looking at the ice, and you know, okay, it's done. Okay, the temperature is, and you write the final temperature down in your lab. Now, there's one other thing that we need at this point. So we can take apart the calculator, turn it off, but now we have a styrofoam cup. And you're going to take the styrofoam cup full of water, and you're going to remeasure how much there is in there. Well, if you're close to 50 to start with, you're going to be over, right? So what you want to do is you're going to put it in till the bottom of the meniscus is right at 50 milliliters. Then you're going to dump it out. Then you're going to pour it in again, and you're going to measure it again. Add those two together for your final. That's all you need. Clean up, put everything back, get a stamp, come back in here and work. Questions? No goggles, no aprons, move fast. Go.